the second floor is about the security networking area, and I believe we have three very interesting parts. The first one is try to change the screen so that we are on the same page. Session 4. So the paper is Zephyr, zero loss and transparent TLS connection migration framework. And this is a joint work from Zhejiang University and Alibaba Zhao. The presenter is also the first author of this paper, Jiazhen. He is currently a third-year PhD, so you're already halfway there. So he's a third-year PhD at the Zhejiang University. His advisor is Dr. Wenzhi Chen. Jiazhen also received his bachelor degree with honor from Zhejiang University. His research focused on the intersection of the system and networks and international in the cloud, with a focus on virtualization, granular networks, and confidential computing. Without further ado, please.
Thank you. Hello everyone, I'm Jiazhen from Zhejiang University. Today I will present my work to Zephyr, the zero loss and non-transparent framework for migrating established TLS connections across nodes. So why do we need the TLS connection migration? Let's begin with the typical cloud service path. A client TLS connection passes through a front-end L7 network function application and before reaching the backend server. And the layer 7 component may be a proxy or a load balancer, like the Enge application. The first motivation is about the seamless maintenance, like the software hot application in the cloud. The conventional approach stops accepting new connections and waits for existing ones to terminate naturally. This is known as the connection draining. However, a long-lived connection may remain active for days or even weeks. So as a result, a routine upgrade may require all instances to remain active for a long time, increasing both resource and operational costs. And after timeout, the operators will terminate these connections, which is also a disaster because we have many stateful services that are sensitive to the connection interruption. For the LLM inference, it will result in the context loss and waste resources to recompute the tokens. And for the LLT devices, simultaneous disconnection will result in the reconnection storm. And for the live streaming apps, the disconnection will cause a video lapse or the video frame loss. Existing works fail to solve these problems very well. The VM or process migration is too cost-free, and the Capybara or the HTTP, they only support TCP connection migration instead of the upper layer TLS or layer 7 protocol states. And more recent works like the Prince or the XO, they drop the packets during the TLS connection migration that downgrade the quality of service and the throughput. And they also have incomplete TLS compatibilities. For example, they rely on the kernel TLS or the lightweight TLS libraries that support only that lacks the support for important features like the zero RET in TLS 1.3, and so they are insufficient for the production usage. To solve these issues, the first challenge is to maintaining the consistency of the inline packets. After the connection is frozen, packets already in the network may still arrive at the destination, delivering them directly to the kernel's TCP stack that has not yet been restored would corrupt the connection states. So the packet buffering system must have sufficient capacity and a flexible, efficient buffer management mechanism to buffer the in-flight packets. Second challenge is about the complexity of the TLS state migration. There are three concrete challenges, and for for the function pointers that store the virtual addresses, they will lose their semantics if we migrated from one machine to another. And also, it's hard to determine the memory footprint of these structures that is dynamically allocated. And finally, identifying connection states from the global states is also difficult since we only want to migrate the per-flow states. Therefore, reconstructing every state is engineerily infeasible. Now, let me introduce the Zephyr's design. Here is the system architecture overview. The MIG-K is a data plane using the eBPF TCX programs for the network address translation, the redirection, and the packet buffering. The MIG-D is a user space daemon for the control plane who manages the migration task, and the MIG-Aux are a set of hook points and primitives for the state serialization and restoration. Our migration protocol includes 4 stages. The first is preparation. So both sides will initialize the eBPF maps and the rules. The second stage is the state transfer. The source will freeze the connection and the serialized states, transfer it to the destination. The third is the restoration phase. The destination L7 network function will restore all the states, including the L7, TLS, and TCP states with the help of the destination MIG-D. And finally, the MIG-D will end the buffer, replace all the packets, and release the resources. Now, let's get more into the zero loss handover mechanism in details. Here is the picture of the buffering workflow. To capture the data sent from the client during the capture phase will be redirected to the destination, and the buffer module in the destination will store those packets in the eBPF maps. During the replay phase, the user space MIG-D will retrieve those packets from the eBPF maps and re-inject those packets to the raw AF packet socket. And for the buffer management, we use the mapping map hierarchy that allows dynamic allocation rather than allocating them before the compilation. For the buffer capacity, we set it to the TCP RMAP maximum, which is the system parameter in the Linux OS that upper bounds the packets the sender can send during the connection. Now, let's go to the next question. How can we restore the TLS states with the minimal intrusion to the open SSL while preserving the transparency of TLS, the transparency to the client? Our insight here is to use the TLS session assumption to reconstruct most states. For example, the state machines for the destination server, and we only inject the key materials we serialize from the old machine. Why does it work? Our observations are as follows. Firstly, the TLS session assumption is usually used when the client wants to reconnect to the same site repeatedly. The client will send a server-issued session ticket to start the TLS session assumption. And on the other hand, after the initial handshake of the connection, the server and client have identical session contexts. Based on these 2 observations, we can construct a fake client because fake client, the states needed for the fake client basically equals to the server session context and the server session ticket. So we construct such a fake client to init the TLS session assumption on the destination node to help the L7NF to reconstruct its TLS states. Here is the restoration workflow of Zephyr. After the connection is freezed, the source will send all the connection states, including the session ticket, session context, key materials, TCP, and upper layer states to the destination MIG-D. Here is the layout of the destination node. The MIG-D will construct a fake client based on the session ticket and session context, and then release other states to the L7NF. The L7NF then initializes the TLS object. After that, the MACD will let the fake client to request to resume the session, TLS session by sending a client hello carrying a session ticket. After this handshake, the L7F restores its most states. Its following work is to inject all the key materials and restore the TCP connection. The final step of this workflow is to reband the circuit from the connection between the MACD to RNF to the real data path and notifies the finish to the MACD. Our preliminary evaluation shows that the end-to-end migration latency for an idle connection is about 4.4 milliseconds, of which fake client handshake takes about 40%, and the EPPF operations takes only about 8% of the total time. This breakdown shows that the operations on the kernel data path is not a bottleneck of the migration. We also evaluate this framework on its network performance implications. The latency we introduce for the request latency is about 4.5 milliseconds back, which is basically equals to the latency of the migration process. And since we guarantee the zero loss feature during the migration, we do not cause any retransmissions. The retransmissions usually would introduce a latency of more than 200 milliseconds. On the other hand, as for the throughput only drops during the migration and behaves as before immediately after the migration. Yeah, that's all for this paper. And beyond that, we are also trying to extend Zephyr from a prototype to a deployable framework in the cloud. We try to extend the protocol compatibilities by supporting Lexi TLS 1.2 and more stateful L7 protocols, such as the WebSocket and HTTP2. We are optimizing the control plane coordination for the production scale migration batches. And we are also trying to add a failure-safe rollback mechanism to this framework. To conclude, Zephyr achieves the following properties. The first is the zero loss handover. All the in-flight packets arriving during the migration are not be dropped. Here's a mistake in the PPT. And the second is the client transparency. The migration process is transparent to the client endpoint, and there is no need for the modification of any client software. Thirdly, we have broad compatibility. The framework integrates with the standard production-grade software stacks like OpenSSL and Linux. Thank you all for listening.
Any questions? Maybe I will start a quick question. So if you could go back to the restoration workflow page.
Yeah.
Okay. Here's I noticed you assume all components work without any privilege compromise.
Yes.
So how hard is it to satisfy this assumption?
It's a common assumption because we do not assume the OS is compromised or something like that. So the communication channels we use for the communication channels in the same machine we use the Unix domain socket. We can trust it, yeah, if the OS is not compromised. And for the communications between the machines, we use the encrypted channels, like we use the TLS to encrypt the information. So if we are in a trusted environment in the cloud, all the machines are owned by the cloud service provider, so we can trust all the machines and the communication channels among these. Yeah.
So for your preliminary evaluation, so can you go to that slide, the evaluation?
Evaluation? Yeah. This one? Yeah.
So the throughput, yeah, I probably missed something, but if you during the migration with the sender keeps sending the traffic,
yeah,
and but during the process of migration, where would these new flag packets be stored? They are dropped or they are stored in one?
They are stored in the eBPF maps, and after the migration, we retrieve it from those maps and re-inject it to the TCP stack. So there will be a spike of the throughput because it's not fully
From the network.
yeah, from the buffer, yeah.
How much the buffer do you need? To have a solution?
How long?
How large?
Yeah. Here we set it to the TCP RMAN maximum, which is a system parameters in Linux OS. Yeah, it's a upper bound of the TCP receive window. Yeah, so the client will not send any other packets if it reaches the point if the non-acknowledged data reaches this point. Yes.
Other questions? If not, let's start the speaker again for the part.
Thank you.